Imagine you're standing in a quiet room. On a table in front of you sits an ordinary wine glass. Nothing unusual. Nothing special. Now imagine you begin to sing. You try one musical note. Nothing happens. You try another. Again, almost nothing. Another. Still no visible response. Thousands of different sound waves can strike this glass without causing any noticeable effect. But then, something extraordinary happens. You accidentally sing one very specific note. Suddenly, the glass begins to vibrate. At first, the motion is tiny. Almost impossible to notice. But every new sound wave arrives at exactly the right moment. Each vibration adds to the previous one. The motion grows larger and larger. No one touched it. Nothing ever made physical contact with the glass. Only sound. Why? Why did one note succeed, while thousands of others failed? The answer begins with one of the most beautiful ideas in mathematics. An idea engineers used to design bridges, aircraft, electric motors, spacecraft, and earthquake-resistant buildings. That idea is called an eigenvalue. But if I simply wrote an equation on the screen right now, you might memorize it. You probably wouldn't understand it. So instead, let's discover the idea the same way nature does. To answer that question, we first need to understand what a transformation really is. Imagine a mysterious machine. Whatever enters this machine comes out different. Today, we're only going to feed one type of object into it. Arrows. An arrow has only two important properties: its length and its direction. Let's see what our machine does. We place one arrow inside, and it comes out pointing somewhere else. Interesting. Let's try another. Different again. Another. Again. Some arrows become longer. Others become shorter. Most rotate into completely different directions. At first, everything seems random. It almost looks as if this machine refuses to let any arrow keep its original direction. If you watched only these examples, you'd probably conclude that every arrow must rotate. That seems perfectly reasonable. But watch carefully. We're about to discover something unexpected. Everything we've seen so far seems to suggest one simple rule. Every arrow changes direction. Every arrow rotates. At least, that's what it looks like. But let's test one more direction. Watch this arrow carefully. The machine transforms it. Something changes, the arrow becomes longer. But something doesn't change. Its direction. Let's try again. Exactly the same thing happens. The arrow stretches, but it refuses to rotate. One more time. Longer. Still no rotation. Out of infinitely many possible directions, this one behaves differently. Let's compare it with an ordinary arrow. This blue arrow rotates immediately. Its direction changes. Now compare that with our golden arrow. It grows, it shrinks, it can even flip around. But it never leaves its own line. That line is its identity. Mathematicians gave these special directions a name. They are called eigenvectors. Not because they are magical. Not because they are rare. But because they preserve something that every other vector loses. Their direction. Finding the special direction solves only half of our mystery. Something else changed every time the machine acted. not the direction. The length. Exactly how much did it stretch? That number turns out to be just as important as the direction itself. Let's focus only on our golden arrow. Forget every other vector. Suppose its original length is 2 units. The machine transforms it, and now its length becomes 6. Nothing happened to its direction. Only its size changed. How much larger did it become? Exactly 3 times. That number, 3, is our first eigenvalue. Let's try another example, a different machine this time. Our arrow starts with a length of 4. The machine transforms it, and now it measures only 2. Again, its direction stays exactly the same. This machine multiplied the vector by 1/2. So the eigenvalue is 1/2. Now let's see something even more interesting. Watch carefully. The arrow transforms again. It stays on the same line, but now it points in the opposite direction. What happened? The machine multiplied it by -2. Twice as long, but because the multiplier was negative, its direction flipped. Notice something important. Even though the arrow reversed, it never left its own line. So this is still an eigenvector. An eigenvalue can be positive. It can be smaller than 1. It can even be negative. The sign changes the orientation. The magnitude changes the length. But the line remains exactly the same. So here's the beautiful idea. The eigenvector tells us where the transformation prefers to happen. The eigenvalue tells us how much that transformation happens. Direction and stretching. Together, they describe one of nature's favorite motions. At this point, we've discovered everything visually. A special direction. A special stretching factor. Engineers don't usually draw arrows like this. Instead, they summarize everything we've just learned, using one surprisingly simple equation. Everything we've discovered so far can be summarized by one remarkably simple equation. At first glance it may look intimidating. But now, every symbol already has a meaning. Let's read it from left to right. The letter A represents our transformation machine. It takes an input vector and transforms it. The symbol V represents our special vector. Not just any vector. The one that refused to change direction. The one we called the eigenvector. Finally, the Greek letter lambda. Lambda is the stretching factor. If lambda is 3, the vector becomes 3 times longer. If lambda is 1/2, it shrinks to half its length. If lambda is -2, it doubles in size while reversing its direction. That's all this equation is saying. The matrix transforms the eigenvector, and the result is exactly the same as simply multiplying that vector by one number. Notice something important. The equation never says that every vector behaves this way. Only the special ones. That is why eigenvectors are so valuable. They reveal the hidden structure inside every transformation. This single equation looks small, but it quietly explains an astonishing number of engineering problems. So far, everything we've explored has lived inside mathematics. But here's something remarkable. Nature solves this equation without ever learning linear algebra. Let's see what happens when mathematics becomes physics. Imagine 2 masses, connected by springs. Push one of the masses. At first, the motion looks completely chaotic. Every mass moves differently. Everything seems unpredictable. But if we watch carefully, something fascinating begins to happen. certain patterns start appearing. The entire system begins moving together. Not randomly, but in organized shapes. Here is the first one. Both masses move together, in the same direction. Now watch another pattern. One mass moves one way, while the other moves opposite. Completely different. Yet equally natural. These aren't motions we invented. The system chose them. Left alone, every vibrating structure naturally prefers these patterns. Engineers call them mode shapes. And here's the surprising connection. Every mode shape is an eigenvector. Each one has its own eigenvalue. And in vibration problems, that eigenvalue determines the square of the natural frequency. The mathematics we just learned with simple arrows is exactly the same mathematics governing vibrating machines, bridges, aircraft, and buildings. Nature has been solving eigenvalue problems long before humans discovered linear algebra. The spring system was only the beginning. Every physical structure has its own preferred ways of vibrating. Let's see how the same mathematics appears everywhere. By now, you've seen eigenvalues in simple arrows. You've seen them in vibrating springs. But those are only the beginning. Consider an aircraft wing. As the airplane flies faster, air flows around the wing and the wing begins to vibrate. Most vibrations disappear quickly. But some patterns naturally grow stronger. Those special patterns are determined by eigenvalues. Now look at a skyscraper. When an earthquake strikes, the building doesn't move randomly. It vibrates in its natural mode shapes. Those mode shapes are eigenvectors. Their frequencies come from eigenvalues. Let's return to the question that started everything. At the beginning of this video, we watched a singer shatter a wine glass. Now, we finally understand why. Every object has natural frequencies, set by its shape, its stiffness, and its mass. Most sound waves fail to match those frequencies. Their energy never accumulates. The vibration remains small. But one very special note matches one of the glass's natural frequencies almost perfectly. Each new sound wave arrives at exactly the right moment. Instead of canceling the previous vibration, it reinforces it. Energy keeps accumulating. The vibration becomes larger. Then larger still. Until the stress inside the glass exceeds its strength, and the glass breaks. Not because the sound was extremely loud, but because the frequency was exactly right. That phenomenon is called resonance. And resonance is one of the most important consequences of eigenvalues in engineering. Understanding these natural frequencies lets engineers avoid dangerous vibrations before they ever happen. Let's summarize everything we've learned. A matrix transforms vectors. Most vectors change direction. A few special directions never do. Those are eigenvectors. Each eigenvector has its own stretching factor. That factor is the eigenvalue. When mathematics meets physics, those eigenvectors become vibration mode shapes. Those eigenvalues become natural frequencies. Together, they explain why structures vibrate the way they do. Why bridges sway. Why aircraft flutter. Why buildings respond to earthquakes. Why guitar strings produce musical notes. And why one perfectly chosen note can shatter a wine glass. One mathematical idea. Countless engineering applications. That's the power of eigenvalues. The next time you hear the word eigenvalue, don't think of a difficult chapter in linear algebra. Think of a bridge dancing in the wind. Think of a skyscraper surviving an earthquake. Think of an aircraft wing vibrating in flight. And think of a single musical note, powerful enough to shatter glass. Nature has been using eigenvalues long before humans gave them a name. The code behind every animation in this video is free on the GitHub below. No black box. Run it yourself.